Alright guys, welcome to test 3 for fluid mechanics. First off, we have the multiple choice, which is 1A through 1E. The Reynolds number can be interpreted as the ratio of inertial to viscous forces. Right here, I have the Reynolds number for us. We have density, velocity, length over our viscous, our viscous. What is that called? It's mu. I know it's mu, but it's dynamic viscosity? No, that's the other one. This is dynamic. Which one's dynamic? Dynamic viscosity is the... yeah. Dynamic, okay. So this one is kinematic viscosity, this one is dynamic. Kinematic means when it's moving, dynamic means when it's not. Alright, and the ratio of inertial to viscous forces. So the viscous force is on the bottom. It's always on the bottom, even over here when you substitute in the kinematic viscosity. So what's on top? It's gotta be the inertial forces, because I mean, inertial, the velocity times the density times the length is probably gonna give a certain amount of force. Okay, number 2, we test model devices rather than real or prototype devices because it is less expensive to test models. Fully developed flow in a pipe means the velocity profile is the same in every section. So if this is the entrance region, and then as you get into a fully developed flow, it's a parabola, and it's the same in every region, I guess. For fully developed viscous flow in a horizontal pipe, which of the following is true? Or which is true? And the answer is pressure forces are balanced by shear forces. So once you get here and you have viscosity to deal with, the viscosity and the stuff makes the pressure make turbulent flow, but since they cancel each other out, are balanced by each other, it becomes laminar flow. Unless you're going really, really fast, or, you know, it's a really, really big diameter, or the viscosity is just crazy, like oil or like honey. The density being high helps it, or well, actually, the viscosity being, it's like, yeah. Honey has a really high viscosity, so that means the Reynolds number will be smaller because of it. Density, though, I wonder if honey is more dense than water. Probably. But water has a density of 1,000 kilograms per 1,000 something. For steady flow of an incompressible liquid in a pipe, which of the following is true for the entrance region? So this is this pipe, and it's the maximum velocity increases with distance from the entrance. Because the entrance has a low pressure most of the time, it's coming from like a large entrance region, and using like Bernoulli's equation, when you go from a large, low pressure to a really, it's a higher pressure, and then you go to a lower pressure because, they balance each other out. So it's a higher pressure in the entrance region, because I mean, it's a bigger thing. And then when you get into the pipe, it's a higher velocity and a lower pressure. Yeah, I'm sorry, I got that all mixed up. Right, on to question 2. Okay guys, so an oil flows steadily through the 1-inch gap between 2 fixed horizontal parallel plates. The width of the plates is 2 feet. A manometer indicates a differential reading of 10 inches. the specific weight of the manometer fluid is 100 pounds over feet cubed. So here's that, here's the width, here's the viscosity, dynamic viscosity, here's the specific weight of the oil, which is 50, 100, and this is 0.02. It's kind of hard to read. This is 0.02. And for part A, we're trying to find delta P. There is also part C, Reynolds number. Okay, so for part A, we're determining the pressure drop from A to B. And then calculate the volume flow rate per unit width, which is the small q, and then the volume flow rate, which is the big Q. And for C, we calculate the Reynolds number of the oil flow, and is the flow laminar. Explain. You don't really have to explain, but yeah. Okay, so for part A, we use the manometer rule, where it's the pressure of A plus the specific weight, which is the density times the gravity times the distance, minus this one, the specific weight of the manometer, times the height, or delta x, minus the specific weight of the oil times the same thing over here, minus delta x. It's equal to the pressure at B. So if we were calculating just PA, it would be this on this side, and then this stuff is on with PB, because that's what side it is on. But once you do some algebra, PB minus PA or PA minus PB, I don't think it really matters. But it's the height, or delta x, and our height right here is 10 inches. It's kind of hard to see, but times the specific weight of the manometer fluid minus the specific weight of the oil. That's probably not a great explanation, but after doing all that, we get 100 minus 50, and that's in pounds over feet cubed. That's not in pounds over feet cubed, is it? It is. Well, I'm wrong. Times are 10 inches, but you gotta divide by 12 to make it feet. So our delta P is going to be equal to 0.29 psi. Okay, now on to the next question. What? Oh, we aren't working in PSI. That's why I wrote the wrong thing. It's 41.67 pounds per feet cubed, squared. And next we are going to find the volume flow rate per unit width, which is small q, and we have our equation right here. We have our equation right here. 2h to the cubed, delta P, 3 dynamic viscosity of the oil times the length. The length is 6, the h, which is the gap, so this is the space in between two plates, so it's a gap, it's not a diameter. So the h is the middle point for some reason, so it's the gap divided by 2, so it's 0.5 inches. So what we get is 2/3 times 0.5 over 12 cubed times 41. But yeah, that's in feet cubed, times 41.67 pounds over feet squared over, the 2 is on the top. 3 is a lot. The dynamic, which is 0.02 pounds times second over feet squared, times the length. And the length is 6 inches, so it's 1/2, but I'll just write 6 over 12. And that's going to be 0.2. And that's in feet squared over seconds. I did my dimensions wrong in my original problem and I got feet cubed, so, you know, we live and we learn. Alright, so our next problem is Q, big Q. And that's just Q times the width, and we have our width, which is 2 feet, so it's just 0.2 times that. So 0.2 times 2, and then it's feet cubed over second, because it's the volume flow rate. And what is that, 0.4? Yeah, just 2 times 0.2. 0.4. I messed up on this point. I put it's the gap times Q instead of width times Q, which is my fault, honestly. And the gap, how did I mess up what the gap is? I messed up what the gap is. The gap, even though I did it correctly on the finding Q point, I did it wrong for this, which is pretty funny. But next part of the problem, we have to find Reynolds number, which, if y'all remember, is RE equals, what is it? Density, velocity times the length or the diameter over the viscosity. So RA is equal to VL over mu. So what we get is, what's the density? Oh, we have to solve for the density. Over G is equal to P, so that's going to be 50 over 32.2 is equal to, why did I not write anything down? It's 1.55. And that's in pounds times seconds squared over feet. Right? Yes. No, it's not second squared. It's feet squared. How do I keep messing things up? I don't know, because you have, oh, I did the specific gravity wrong. I put it as pounds over feet cubed right here for 50. And yeah, we are working for the oil. Because that's, we're not looking for the Reynolds number, we're looking for the Reynolds number of the thing flowing, and that's the oil. So that is equal to 1.5, oh, no, that's, wait, what? How did I mess up? What? Oh yeah, and you have to solve for the velocity. How did I mess this up, bro? 1.55, and that's pounds over feet cubed, right? They didn't do it. It's pounds over feet cubed. It's pounds times seconds squared over feet to the fourth, which is crazy. Okay, and V is equal to Q times, or is it Q divided by? Q divided by the gap. The gap, so it's 0.2 divided by 1 over 12, which is 2.41 feet per second. And now we have everything. Over 0.02 times not 0.02. What is the next thing? 2.41. And then times the length, which is 6 over 12. No. The length. Oh. It's not the length. It is the diameter. So it's the gap, which is 1 over 12. Yep. And what we get is RE is equal to 15.6, which means our laminar is less than 1400, so flow is laminar. Check. Alright guys, next problem. Okay guys, so this one's an easy one. Well, it's not really easy, but it's easy conceptually. Golf balls must meet a diameter standard of not less than 4.267 centimeters. A ball hit by a professional golfer can reach a speed of 80 meters per second and an angular rotation speed of 8,000 revolutions per minute. Determine the diameter of the model of the golf ball to use in a wind tunnel with a maximum speed of 25 meters per second. The lift and drag of a golf ball are functions of the Reynolds number in a dimensionless group that includes the rotational speed. Pi equals WD over V, where W is the rotational speed, D is the diameter of the ball, and V is the velocity. Use Reynolds numbers, similitude, and dimensional group that includes rotational speed similitude to determine the diameter and rotational speed for the ball. So that's these two, rotational speed and diameter. Assume that the air properties are the same for both the prototype and the model. So what we get is similitude is just the prototype is equal to the model, and since our properties of air are the same, the density of the air is the same, so we can cancel that out. This is Reynolds number, so we make the model equal to the prototype, and we can also cancel out the viscosity. So what we get is the VL of the prototype is equal to the VL of the model. So we get 25 meters per second times L is equal to, well, our L is going to be our D. Times 80 meters per second times 4.6, what? Why is it divided? Oh, never mind. 4.267. It's kind of hard to read, but whatever. So our L is equal to 13, and this is the diameter of the model, is equal to 13.65 centimeters. Okay, now we look for the rotational speed, and luckily they give us this one. So look for a model, and that's the velocity of the model over velocity of the prototype. Diameter of the prototype over diameter of the model. Right. No. Yes. 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 Okay. And then W of the prototype. Yep. So what we get is 25 over 80, 4.267 over 13.65 times 8,000 is equal to the rotational speed, which is in revolutions per minute, and that's 781.5 RPM. Okay guys, that's similitude. It's one of the easier things. So on to the next question. Okay, on to problem 4. So the flow rate Q of corn syrup through a horizontal pipe shown in the figure below is to be monitored by measuring the pressure difference between sections 1 and 2. Take Q as 0.7. Oh, I put 0.7. 0.7. Feet cubed per second. Length as L is equal to 6 feet. Viscosity is equal to 4.2 times 10 to the negative third. Density is 2.3. Calculate A, Reynolds number, is the flow laminar. B, the pressure drop, delta P. Calculate the tau, the wall shear stress, which is tau of W. So, first off, we have to find the velocity. So that's pretty easy because it's 0.7 over pi over 4 times 0.25 squared. And that's going to be how did I do that wrong? I must have done the algebra wrong. I must have put it in my calculator incorrectly. That sucks. 14.26 feet per second. And then we have the density. The density is 2.3 times 14.26 times the diameter, which is 0.25. So the diameter is 3 inches, but we divide by 12, and that's 1/4, so 0.25. And then the dynamic viscosity, which is what, 12? No, it's 4.2 times 10 to the negative third. And the density is in slugs per feet cubed. The velocity is feet over second. Diameter is feet. The viscosity is pounds times second over feet squared. And what that gives us is 1952.26. How did I mess that up? Must have put it in my calculator wrong, like for real. But anyway, I still got the right answer. So 19,000. So RE, the Reynolds number is below 2100. This is for flow in a pipe, so it's a different number for each one. So it is laminar. So for B, let me erase this. For B, we have our specific equation, and that is delta P is equal to 128 mu L A. What is A? Oh, Q. Mu L Q over BD? No, pi. Pi D fourth. So what we get once we plug all that in is 128, 2 point, let me just pick this up. Oh, that's so much easier. 4.2 times 10 to the negative third times 6, because our length is 6 feet, and then our q, which is 0.7, and that is all over pi 0.25 to the cube. No, sorry, to the quadratic. What is that? Fourth? Yeah, it's just the fourth, not cube. So after doing that, you get 184 pounds per feet squared. And then if you divide by 144, you get 1.28 psi. It doesn't ask you to, but we did in this case. Okay, and C, we have another equation, which is delta P is equal to 4L tau of the wall, which is the shear stress, times D. And what that is, so yeah, tau of the wall is equal to delta P times D over 4L. And that's... No, I spilled it again. Is that the second time in the video? That's funny. That's pretty funny. Always remember to put your cap on your water bottle, because I keep forgetting and I keep putting it right by my feet while I'm making these videos. Put the cap on. So we use 184. Yeah, I don't know why they converted to PSI. 4 times 0.25 over 4 times 6, and what that gives us is 1.92. 92 pounds per feet squared. Alright, that's question 4. On to question 5. Okay guys, so this is problem 5, which is the last problem. And our question is, oil with density 900 kilograms per meters to the cube and kinematic viscosity 0.0001, 4 zeros, meters squared over second, flows at a rate of 0.2 meters cubed over second through a 200 millimeter diameter cast iron pipe. The pipe has a length of 500 meters and is inclined. It slopes down at 10 degrees. They put a 0, which really confused the heck out of me on the test, in the flow direction. A, calculate the entrance length. B, determine the friction factor and the head loss. And then C, use the energy equation to find the pressure drop. Okay, so first off, we have to calculate Reynolds number. Reynolds number is V velocity times diameter over kinematic viscosity. So first off, we have to find this, which is Q. They gave us a Q at 0.2. Yeah. 0.2 over pi over 4 times D, which is 0.2 squared. So it's pretty much 0.2. It's 1 over pi over 4 times 0.2, which equals 6.367 meters per second. Nice that we're working on meters on this one. Working in feet is such a pain, man. Okay, now for Reynolds number, which is pretty easy for this one. 6.367 meters over second times 0.2 meters over 0.00001. What is that in? It's in meters squared over seconds. Okay, so after doing that, we get a Reynolds number of, what is it? 1.27 times 10 to the 5th. Now, looking at that, it's 10 to the 5th. So it's not going to be laminar, because for it to be laminar, RE has to be 4,000. Is it 4,100 or just 4,000? Just 4,000. And they give the laminar number on the sheet. So it's turbulent. Okay, from that, we need to then find the entrance length of the region. So that's 0.2 meters times 4.4 times the Reynolds number, which is 1.27 times 10 to the 5th times 1 to the 6. Or it's the power of 1 over 6. And that gives us, it's kind of at an angle, so it's 0.2, 4.4, 1.27 times 10 to the 5th. Repeating myself. What does that give us? 6.24 meters. And that is the length of the entrance region. Next we need to find, so on your equation sheet, they're going to give you a diagram of cast iron, plastic, a bunch of other stuff. And this roughness principle for cast iron is E equals 0.26 millimeters. And then that 0.26 millimeters divided by what is our 200 millimeters is equal to 0.013. Next, we use the Moody diagram, or the Holland equation, and we have to find F, which, let me pull out a Moody diagram real quick. It's right here. Yeah, here we go. So this is our Moody diagram. Oh, it's upside down. So this is your Reynolds number. This is your epsilon over D. This is your F. So since we're in turbulent, we're above this line. So using this, we have a epsilon over D of 0.0013. So that's right about here. It's right about right here. And we go all the way over here. And then the Reynolds number is 1.27 times 10 to the 5th. So that's right here. Oh, right here, I think. 10 to the 5th, 2, 1. So going up, get around here, and our F is going to be, it's like 0. Okay, so I was going to say 0.02, and I'm right. But the specific, if you use the Holland equation, is 225. Okay, now we have to find the head loss. So the head loss is, they have HL major and HL minor, and there are different equations. Give me that equation, Jake. HL minor is KL V squared over 2G, but I don't think we have any in this one. So we just mark it as HL major. So it's equal to F, that's not F, that's P. F times L over D V squared over 2G. So we have our 0.025, 0.2225 times our length, which is 500 meters. Oh yeah. 500 meters, that's the length of this whole thing. And D is 0.2 meters. Velocity is up here, 6.367 meters over second squared over 2 times 9.81 meters over second squared. No, this is squared. And what we get from doing that is HL major is 116.32? No, 22 meters. Okay, and now we have to do the energy equation. So we did this back on the last test. Y'all can rewind. Y'all don't need me to tell y'all to do that. So we can now do the energy equation, and most of it's canceled out, which is nice. But we get I'm gonna do this one. Pn. Oh man, this marker. This is why I didn't want to use this marker, because it's almost out. It's still working, but it's almost out. And if you draw the wrong way, it doesn't come out at all. Yeah, see, that looks sloppy. Where's my other marker? Just had it. Here it is. Whatever. It's not gonna kill me if I just raise it with my hands. So, Pn over specific gravity plus v squared over 2g plus zn plus h, what is this, hs? No, hp equals same thing, p out over specific gravity plus v squared out 2g plus z out plus HL plus HT. Yep. Okay, so most of these are not in the equation. So we're trying to calculate delta P. So we need both of the pressures, but we have a Vn, which is 6.6. Oh no, we cancel the. Why do we cancel the one that goes in? I don't know, but we do. Good question. Why do we cancel the one that goes in? Because it's a large reservoir. That's what they usually say when you have a big thing connecting to a small thing, and the velocity going in, it just doesn't matter because there's an infinite amount or something. The Zn does matter. HP does matter. Oh no, it doesn't matter. We don't have a pump. No pump, so no HP. P out, we need that. V out, we don't need that, because when you're going out, it's going to free atmosphere, so we don't care about that. And then Z out, we don't care about that because it's 0. And then HL, we do care about that, and HT is something I don't even know about, but that's okay. Don't tell anybody. So what we get what we get is delta P is equal to, what is it? Specific gravity times HL minus Cn. Because that's because we minus that, we multiply by specific gravity, and that's the only other thing on that side. So it's HL minus Cn times specific gravity. Yeah, makes sense. Specific gravity is 1,000, or is it 1,000? It's 900. They gave us a density. 900 times 9.81 times, what was our 118? 116.22. Oh yeah. Minus our Zn, and we calculated our Zn earlier. Our Z out equals 0. I'm just gonna erase that. Our Zn is the distance right here, and that's just a right triangle. So we just use sine of 10 degrees times 500, and that gives us 86.8. Well, 824. And then we subtract that, and we get a delta P value of 259.5 kilopascals, which is quite a bit. Honestly, let me look up HT before I end, because I'm really curious. What is HT in the energy equation? Fluids. HT typically it represents the total specific enthalpy of the fluid. I don't think that's right. That's AI saying that. I don't think that's right though. That is NASA. Turbine. Ah, that's it. It's so the HP is the pump, HT is the turbine, HL is the loss of the like power. Okay guys, that's it for test 3. Quite short comparatively, but you know, we gotta get it done. Hope y'all enjoyed test 3. I'll catch y'all in the next one.